My name is Jim Lerner. I'm the country manager here in the US, and I have one of the experts here in the world, Christian Born. Welcome.
Hi everyone, nice to be here.
So we were going to talk about the 7 harmonic issues that could be called harmonics, or what we are calling harmonics. So what do you say about the first one? That's really what we call harmonics. What is really that?
Okay, the problems that we're talking is power quality issues, and one of them is harmonics. So we have a bunch of different power quality issues that we see in an electric grid. Of course, the electricity is not perfect. There is a problem with all different kind of things. And yes, the biggest one that we're seeing nowadays is harmonics. Harmonics is simply a multiple of the fundamental frequency. So ideally what we want to have in the grid is the 50 or 60 hertz waveform and nothing else. What we're getting in practice is other additional waveforms, higher frequency waveforms on the voltage and on the current as well. And these are harmonics. They are typically a multiple of the fundamental frequency. There can be also other things like in between these multiple of the fundamental frequency. And this harmonic is what causes today the biggest problem. We have these harmonics simply because of the fact that we are using a lot of frequency converters or converters in general from AC to DC, like for the lights and other equipment like that. But the big factor is simply frequency converters, like you use to control whatever motor you have, if it's a pump or a fan or an HVAC system or whatever else you have. The motor is simply controlled by the VFD. And the VFD is first converting from AC into DC, creating harmonics in that moment, and then going from AC to from a DC to a new AC, and that new AC is then the frequency that the motor should spin at.
Very good. So power quality. We have the second one then, the reactive power. What is that about?
So yeah, in the past we had more problems on the reactive power than we had on harmonics, simply because we used the motors and we connected them directly to the grid across the line, what we call it here in the US, or direct online load, like we call it in Europe, or it's just a direct motor that's connected to the grid. Now this motor, if you look at the motor, it's actually a bunch of inductance. There's just a lot of wire in there, so we have a big inductance. That means, of course, we're having power because we're running the motor, we're turning the motor, but we're also getting a large amount of reactive power, inductive reactive power. And what we do so far, or what a typical way of approaching that is by installing a capacitor bank, because the capacitor is also creating reactive power, but in the opposite direction of an inductor, and that way we can get rid of this reactive power. Now, we moved a little bit away from a problem with the reactive power, and we moved it over towards the harmonics. So today, harmonics is a bigger problem than the reactive power, because we moved all of these motors away from a direct motor into a frequency drive controlled motor. That doesn't mean that reactive power is disappearing entirely. I mean, yes, if you have a motor connected via VFD, you do not have reactive power anymore. I mean, you might have a power factor of 0.97 or something like that, but more or less there is not much reactive power left. However, we're running in the opposite direction now. So what we're seeing today is a large amount of drives installed in applications, like for example, we have that in airports with their luggage handling systems. And these large numbers of drives all have an EMC filter in front, and all of these EMC filters will have capacitors inside. And these capacitors are now creating capacitive reactive power. So we're actually going in the opposite direction with the reactive power compared to what we had in the past. In the past it was mostly inductive. Now we're turning more and more into the reactive part. And that part can actually also be connected to another power quality issue. and that is now the resonances. Should I just talk directly about that?
Sure. When you're going, go.
Yeah, when I'm going, I'm going. Awesome. So because we have now in the reactive power a lot of capacitors installed, a capacitor and an inductor, they are creating together a resonance frequency where the impedance is in a way that things can get really, really bad. And the inductor is always there. You always have a grid. You always have a motor or something else. Sorry, not a transformer or something else in the grid. So you have this inductance there. And then you have the capacitance. Usually also something there, like just a cable can be a capacitance. But now we have a lot of EMC filters. And all of these additional EMC filters, all these capacitors, will move the resonance frequency further down in the frequency. And I mean, ideally we want to have it far away where it doesn't make any problems, but now it moves further down and it moves in a range where we have already strong amount of harmonics that can stimulate these resonances. So what we're getting is a big swing in the waveform, in the voltage and the current waveform, simply because of the current between the capacitors and the inductors is running back and forth. And because of so much capacitance in the grid, so many capacitors, we're moving the frequency, the resonance frequency down, and we're moving it into a range where we see a lot of harmonic currents already, and with that we're making things even worse.
Yeah. So that's maybe a segue also into the next one of the power quality issues, flicker.
Yeah, you can actually move that over in the next into flicker as well, because yes, all of these things, harmonics, resonances, all of these things are creating flicker, and flicker is just a change in the amplitude of light. The traditional way where we created a lot of flicker was heavy load. So if you have, for example, welding applications or electric arc furnaces, something like that, where you have very large amount of load for a short time, you push that in or pull that from the grid, and suddenly the voltage is dropping down for just half a second or something like that. And if that happens more often, then you will see the light flickering, and it will get into a point where it's getting annoying to you. But yes, also the resonances and the harmonics, they're also creating these issues with the flickering. And I think today we see a bit more of a problem due to harmonics and the resonances, but we also see a bigger problem because essentially what we have now is LED lightings in most of the application. And the flicker was not, the flicker values or the voltage drops that we see, they were not defined based on LED lights, and we don't have a good standard that shows us, hey, what is now with the LED lights, and how do we define the flicker with that? So unfortunately, flickering gets more of a problem as well, and we don't quite know yet how to actually measure it, because the actual measure before was based on normal, or what do you call that, wire lightings. What do you call these lights?
The
traditional light,
incandescent lamp.
Incandescent light
Incandescent
bulbs.
lamp
Exactly.
bulbs, yeah. So yeah, that's pretty thorough here. But then we also kind of a power quality with unbalance in the grid.
Yes.
So
these four that we talked about so far is probably the biggest one. So the biggest one is harmonics. Second biggest one is reactive power. Then we're coming more and more into the resonances and the flicker. So all of these four are the big ones. Now we come to other situation where it depends a little bit on how good your grid is in general, and sometimes you see it more as a problem, sometimes less of a problem. But these the last three, they are not the big power quality issues that are out in the world.
So you're saying good. So I think those that listening here would like to know, what is a good grid?
Yeah, that's very hard to say. So I mean, a good grid essentially is a very strong grid that can provide you as much energy as you need. That is a very strong grid, a very good grid, and that also doesn't act too much based on the the behavior that you have in the grid on your load. I mean, all of these things, if you look at this, they are like the harmonics, we see it first in the current. Reactive power, we see it in the current. Flicker as well, based on the load, we first see that stuff in the current. Also unbalance, we see it in the current. But all of these things in the current is not a big deal. It's not a big problem. Now, if you have a very strong grid, a very big grid that simply says, hey, I have these harmonics, who cares? I'll just provide the current for these harmonics, then everything is super good. But if you have a grid that is a little bit too weak, what will happen is, if you have these harmonics, you will see immediately an effect in the voltage. So you will see these harmonics happening in the voltage as well as in the current.
So can you refer it to IEEE 519 that have the short circuit rating current divided the ratio between the short circuit current and fundamental current? Is that a good?
Absolutely, that's a very good point. We have in the IEEE 519 the short circuit ratio, or SCR, sometimes called in the IEEE 519, and that short circuit ratio is the ratio between the load current and the short circuit current of the grid. And this ratio exactly tells you how good, how strong, or how weak your grid is. The smaller the number, the weaker your grid. The bigger the number, the stronger your grid. So if you have a 5 megawatt grid with a big transformer, 5 megawatt transformer, and only a 50 horsepower drive, then it's a very strong grid in comparison to that very small load. So in that case, we have a very good relation. If we, on the other hand, have a 800 horsepower drive and a 1000 kVA transformer, well, we're a bit more on the lower side on the.
So already in the design phase, you can make a grid good. And what I can see, certain countries even, or certain states in the US, they have different level of stiff grid work or good network. So yeah, it varies.
Yeah, that's very true. I mean, if you look, for example, in Sweden, we have a very strong grid. So we as Comsys, we are coming from Sweden, but we're selling barely anything in Sweden because the grid is so strong. Now we have also the benefit that our regulation, the IEC standards, they're based on voltage distortion as a target level and not based on current distortion as a target level. And because of that, with a strong grid, you have usually a good voltage distortion, and usually you are not running into the issues where you need to have some compensation done.
Mm-hmm. We're coming to one of the last power quality issues here, so voltage variations.
So we have network unbalances, we have voltage variations, and transients as the least important ones. It also again depends on the country. Like network unbalances, also here in the voltage is the bigger problem. In the current is not that big of a problem. But for example, your neighbors to the south in Mexico, they have now a regulation that regulates the network unbalance in the current as well. They simply say, make sure that your network unbalance in the current is X%. I think it's 5% or 2% or whatever it is. I'm not 100% sure. But they want you to make already at that point clear that everything is good. And then, of course, in the voltage, it should be as low as possible. Typically, like in the range of 2% is a reasonable level. Voltage variation, now we come again to the weak grid. If you have a very weak grid, you have more chance of a voltage variation, but also if you have an unstable grid, you have more chance of a voltage variation. So in Europe, we see very seldom a voltage variation problem like coming from the grid. In other countries, we see much bigger problems. Here in the US, it depends a little bit on the state. Of course, some states are better, some are worse.
I have seen a lot of industrial time, during the day, 8 to 5, and then maybe after 5, the voltage goes up. Is that counted into this too?
That is part of the voltage variation, absolutely. I mean, the voltage variation is not just a short term, just for a few seconds or so. That will be seen a little bit more in the flicker compared to the voltage variation. But voltage variation is also over a longer period of time. So for example, at 5, when everyone is going home and shutting down the factory, you're reducing the load, and that overall increases your grid voltage. Quite often what we're doing is we're making sure that during operation hour, we want to have the nominal voltage level. That means during no load, we typically have a bit too high voltage in the grid, and that voltage will then drop down with more load that we're running. So definitely also connected to that part. But in other countries, dips, sags, well, stuff like that can be a bit more problematic. And then the last thing,
Transients.
Transients are happening all the time and everywhere, and transients are simply fast disturbances that's happening like one time, or I don't know, every few hours or something like that. Often it is caused by a big load change. So for example, we have a big motor that starts or stops very quickly, or we are switching in a transformer to the grid. All of these things have very big inrush currents, and that will make quick transients, quick changes in the network. Depending on how the load behaves, the transients might go up or the transients might go down, just depending on the type of the behavior. And then of course you will get extra disturbances on the network because of that.
So it sounds quite bad this. So what's the trend here? Are we getting worse harmonics or power quality issues? Is that the trend, or what's going on?
I would say we're getting more awareness on power quality. So there's more and more people that are getting aware, that seeing that there is an issue in the power quality. I think we had it for a long time that the problems were there, but often the people just said, oh yeah, this machine is just shutting down regularly. It just happens. It's the ghost in the machine. So we know we need to exchange the light bulbs here all the time because they don't work that good here.
Yeah. So the last here, can we do something about it? Can our product, Comsys ADF product, do anything about this?
Absolutely. We have solutions more or less for everything. So all of these power quality issues that you have here, harmonics, reactive power, unbalance, voltage variation to a degree, resonances, flickers, and even transients, we can at least reduce with the active filter or even completely eliminate with an active filter.
That's fantastic.
Yes. Awesome.
Thank you for listening.
Thank you.